4.5 Development leading to the Bohr's atomic model. At the time when different models of atomic structures were being put forth, some result obtained from the studies of interactions of radiations with matter required to be correlated to atomic structures. Niels Bohr utilized this result to get over the drawbacks of Rutherford atomic models. This result were first wave-particle duality of electromagnetic radiations and second line emission spectra of hydrogen. 4.5.1 Wave-particles dualities of electromagnetic radiations. A dilemma was posed by electromagnetic radiations in the world of science. Phenomena such as diffractions and interference of light could be explained by treating light as electromagnetic wave. On the other hand, the black bodies, radiations, or photoelectric effect could not be explained by wave nature of light and could be accounted for by considering particles nature of light. The only way to resolve the dilemma was to accept that light has dual behavior. When light interacts with matter, it behaves as streams of particles called photons. When light propagates, it behaves as an electromagnetic wave. Electromagnetic wave crest, direction of propagation, trough, wavelength, magnetic field, amplitudes. This is the electromagnetic wave. A characteristics of electromagnetic wave, figure 4.4, show a schematic representations of an electromagnetic wave. Various parameters used to describe the different types of electromagnetic radiations are wavelength, frequency, wave number, amplitudes, and velocity. Wavelength, lambda symbol. The distance between two consecutive crusts or trough is called wavelength. It is represented by the symbol wavelength, which is a Greek letter lambda. The SI unit for wavelength is meter m. Frequency. The number of waves that pass a given point in 1 second is called frequency. It is represented by the Greek letters nu. The SI unit of frequency is Hertz, Hz or S inverse. Third, wave number, nu bar. Wave number is a number of wavelength per unit length. Wave number is represented by the symbol nu bar. The commonly used unit for wave number is reciprocal centimeter per centimeter, while the SI unit is per meter. Wave number is related to the wavelength by an expression nu bar is equal to 1 upon lambda. Fourth, amplitude capital A. Amplitude of wave is the height of the crust. Square of the amplitude denotes the intensity of the radiations. Problem 4.4. Visible light has wavelength ranging from 400 nanometer violet to 750 nanometer red. Express this wavelength in terms of frequency Hz. 1 nanometer is equal to 10 raised to minus 9 meter. Solution. C is equal to nu lambda. Nu is equal to C upon lambda. Frequency of violet light is 3 multiplied by 10 raised to 8 meter per second upon 400 multiplied by 10 raised to minus 9 meter is equal to 707.50 10 raised to 14 hertz, and frequency of red light is equal to 3 multiplied by 10 raised to 8 meter per second upon 750 multiplied by 10 raised to minus 9 meter is equal to 4 10 raised to 14 hertz. Different regions of electromagnetic radiation have different value of frequency or wavelength. Thus, the radio frequency region is around 10 raised to 6 Hz. Microwave region is around 10 raised to 10 Hz. Infrared region is around 10 raised to 13 Hz. Ultraviolet region is around 10 raised to 16 Hz. In vacuum, the speed of all the type of electromagnetic radiation is the same, which is 3 multiplied by 10 raised to 8 meter per second, 2.99792 10 raised to 8 meter per second. To be accurate, this is called speed of light and is denoted by the symbol c. The parameter wavelength lambda, frequency nu, and the speed of light c are related by the expression c is equal to nu multiplied by lambda. B. Particle nature of electromagnetic radiation. In the year 1900, Max Planck put forth his quantum theory to explain black body radiation. According to this theory, the energy of electromagnetic radiation depend upon the frequency and not the amplitude. Planck gave the name quantum to the smallest quantity of energy that can be emitted or absorbed in the form of electromagnetic radiations. The energy E of one quantums of radiations is proportional to its frequency nu and given by E is equal to h nu. The proportionality constant h is called Planck constant. Later its value was found out to be 6.626 10 to minus 34 joule second. In the year 1905, Albert Einstein explained the photoelectric effect using Planck's quantum theory. In doing so, he considered electromagnetic radiations as streams of photon of energy h nu. A photon has zero rest mass. Line emission spectrum of hydrogen. When a substance is irradiated with light, it absorbs energy. Atoms, molecules, or ions which have absorbed radiation are said to be excited. Heating can also result in an excited state. When an excited species give away the absorbed energy in the form of radiation, the process is called emission of radiations. The recorded spectrums of this emitted radiation is called emission spectrums. Parameter, sorry, problems. 4.5. Parameters of blue and red light are 400 nanometer and 750 nanometer respectively. Which of the two is of higher energy? Solution. 400 nanometer and 750 nanometer are the wavelength of blue and red light respectively. Energy of radiation is given by the expression E is equal to h nu, and nu the frequency of radiation is related to the wavelength by the expression nu is equal to c lambda, c upon lambda. Therefore, shorter the wavelength lambda, larger the frequency nu, and higher the energy E. This blue light which has shorter lambda 400 nanometer than red light 750 nanometer has higher energy. All of the element hydrogen has the simple emission spectrums. Do you know fluorescent tubes, sodium, vapor lamp, neon sign, halogen lamps are all examples of atomic emissions. When electric discharge is passed through gaseous hydrogen, it emits radiations. Hydrogen emission spectrum was studied by 5 scientists in late 19th century. They recorded the hydrogen emission spectra in different regions of electromagnetic radiation. The spectra were not continuous and comprised of a series of lines corresponding to different frequency. See figure 4.5. Line get closer and closer together and eventually reach the series limits. This is Paschen series infrared, Balmer series partly visible, Lyman series ultraviolet. Figure 4.5 mission line spectrum of hydrogen. In the year 1885, Balmer expressed the wave number of the emission line in the visible regions of electromagnetic radiation by the formula nu bar is equal to 109677 in bracket 1 upon 2 square minus 1 upon n square per centimeter, where n is equal to 345. The line described by the formula are called Balmer series. Rydberg found that all the five series of line could be described by the following general expression. Nu bar is equal to 109677 in bracket 1 upon n1 square minus 1 upon n2 square per centimeter, where n1 is equal to 1, 2, 3, n2 is equal to n1 plus 1, n1 plus 2, n1 plus 3. The value 109677 per centimeter is called Rydberg constant for hydrogen RH. Table 4.5 show the distinctive features of these five series. Table 4.5 Series of emission spectral line for hydrogens. Series Lyman N11 N223 spectral region is violet, ultraviolet. Series Balmer N1 is 2, N2 is 3, 4 spectral region is visible. Paschen series N1 3, N2 is 4, 5 spectral region is infrared. Bracket N1 4, N2 5, 6 spectral region is infrared. Series P1 N1 is 5, N2 is 6, 7 spectral region is infrared. 4.6 Bohr's model for hydrogen atoms. Niels Bohr 1913 put forth his postulates about the atomic model for hydrogen. While doing so, he used the quantum theory wave particles, duality of electromagnetic radiations, and the emission line spectra of hydrogen. 4.6.1 Postulate of Bohr atomic theory. Bohr models of hydrogen atom is based on the following postulate. First, the electron in hydrogen atom can move around the nucleus in one of the many possible circular paths of fixed radius and energy. These paths are called orbits, stationary states, or allowed energy state. These orbits are arranged concentrically around the nucleus in an increasing order of energy. The energy of an electron in the orbit does not change with times. However, the electrons with will move from a lower stationary state to a higher stationary state if and when the required amount of energy is absorbed by the electrons. Electrons is emitted when electrons move from a higher stationary state to a lower one. The energy change does not take place in a continuous manner. Angular momentum. Angular momentum is a product of moment of inertia I and angular velocity omega. Angular momentum is equal to I multiplied by omega, where I is equal to mr square and omega is v upon r. Angular momentum is equal to mr square multiplied by v upon r is equal to mvr. Third, the frequency of radiation absorbed or emitted when transitions occur between two stationary states that differ in energy by delta E is given by the following expressions. Nu is equal to delta E upon H is equal to E2 minus E1 upon H, where E1 and E2 are the energies of lower and higher allowed energy states respectively. This expression is commonly known as Bohr frequency rules. Fourth, the angular momentum of an electron in a given stationary state can be expressed as mvr is equal to n multiplied by h upon 2 pi, where n is equal to 1, 2, 3. Thus, an electron can move only in those orbits for which its angular momentum is integral multiple of h upon 2 pi. Thus, only certain fixed orbits are allowed here. 4.6.2 Result of Bohr theory. Bohr's theory is used to derive the energy of orbit, that is the stationary state in hydrogen atoms. The results of Bohr's theory for hydrogens are summarized here.